perfectly elastic collision in two dimensions. Okay, perfectly elastic collision in two dimensions is that scattering. First laboratory frame. Okay, first laboratory frame. Consider a particle of mass m1 moving with a velocity u1. Consider a particle of mass m1. Consider a particle of mass m1 moving with a velocity u1 vector in the laboratory frame. Okay, in the laboratory frame. Laboratory frame. Okay, okay. Incident particle. This is incident particle. Incident particle. This is incident particle. Okay, and let it have an elastic collision with a particle m2, and let it has an elastic collision with a particle of mass m2 with a particle of mass m2. Okay, at rest. Okay, target particle. This is target particle. Okay, after collision the incident particle, now called the scattered particle. After collision the incident particle now called the scattered particle. Now called the scattered particle. Okay, moves with a velocity v1. Moves with a velocity v1. Moves with a velocity v1. Okay, v1 vector, making an angle theta1. Theta1. Okay, theta1 with the initial direction, and the target particle of mass m2 moves with a velocity. Okay, with the initial direction. Okay, moving with the initial direction, and target particle of mass m2, and the target particle of mass m2 moves with a velocity v2. Making an angle theta2. Okay, with initial direction of motion of m1. Okay, with the initial direction of motion of m1. Okay, let this is the m1 particle. And its velocity is u1. And this is m2 particle. M2 particle at rest. M2 particle at rest, and this condition is before collision. Okay, This condition is before collision, okay? And after collision, this is the x-axis. This is the x-axis. X-axis. This is x-axis, and this is the direction of v1 vector, and this is the direction of v2 vector. This is the direction of v2 vector, okay? This is the theta 1 and this is the theta 2. This is the theta 1 and this is the theta 2, okay? This is the mass m1, and this is y-axis. This is y-axis, and this is mass m2. This is mass m2, okay? The direction of motion of m1. This is the direction of motion of m1. Direction of motion of m1, okay? This condition is after collision. 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 This condition is after collision, okay? Okay? And next is angle of scattering. Angle of scattering. This is angle of scattering. What is angle of scattering? 1 minute. Angle of scattering, okay? 1 minute. Angle of scattering. Angle of scattering, okay? The angle theta 1 is known as an angle of scattering, okay? Theta 1. The angle theta 1 is known as the angle theta 1 is known as angle of scattering. Angle of scattering, okay? Angle of scattering, okay? It is defined as the angle between the initial direction, the angle between the initial direction, okay? The angle between the initial direction, and final direction, and final direction, okay? And final direction, okay? The angle theta 1 is known as the angle of scattering. It is defined as the angle between the initial direction, and final direction of the incident particle, okay? Incident particle, okay? Of scattered particles, are scattered particle, okay? After it has gone up far away, after it has gone far away, okay? Far away, okay? Recoil angle, okay? Recoil angle. The angle theta 2 is known as recoil angle. The angle theta 2 is called recoil angle. Okay? Recoil angle. The angle theta 2 is called recoil angle, okay? And it is defined as the angle between the direction of target, the angle angle between the angle between the direction of target, between the direction of target are require particle after collision, particle after collision and initial direction of the incident particle okay, of the incident particle. Suppose the initial path of the particle M1 is along the x-axis and also the plane containing U1 vector, and V1 is the xy plane. Then according to the principle of conservation of momentum, okay, according to the principle of conservation of momentum, M1 V1 cos theta 1 plus M2 V2 cos theta 2 equal to M1 U1 because suppose the initial path of the particle, okay, M1 is along the x-axis, and also the plane containing U1 vector and V1 vector, this is U1 vector and V1 vector, V1 vector is the xy plane, then according to the principle of conservation of momentum, M1 V1 cos theta 1 plus M2 V2 cos theta 2 equal to M1 U1, okay, and M1 V1 sin theta 1 minus M2 V2 sin theta 2 equal to 0, because before collision the y component of momentum is 0, because before collision the y component of momentum is 0. The y component of momentum is 0, okay, is 0. As the collision is perfectly elastic, the total kinetic energy is also conserved. Okay. As the collision is perfectly elastic, as the collision is perfectly elastic, then the total kinetic energy is also conserved. So 1 upon 2 M1 V1 square plus 1 upon 2 M2 V2 square equal to 1 upon 2 M1 E1 square. This is the equation number third. This is the equation number first, and this is equation number second. Okay. The three equation 1, 2 and 3 contain four unknown quantities b1, b2, theta 1, theta 2. To find the solution of these equation at least one of these must be known. Let us suppose theta 1 is known. Okay, let us suppose theta 1 is known. Theta 1 is known. Okay, known. For simplicity, we further assume that we assume that we assume that assume that we assume that we assume that we assume that m1 equal to m2 equal to m. Okay, hence the equation first, second, third become b1 cos theta 1 plus b2 cos theta 2 equal to u1, and b1 sin theta 1 minus b2 sin theta 2 equal to 0, and b1 square plus b2 square equal to u1 square. Okay, this is the equation number 4th, and this is the equation number 5th, and this is the equation number 6. Okay, this is the equation number 6. Okay, rearranging we get u1 minus b1 cos theta 1 equal to b2 cos theta 2 equal to b2 cos theta 2. Okay, and b1 sin theta 1 equal to b2 sin theta 2, and u1 square minus b1 square equal to b2 square. This is the equation number. This is equation number. This is the equation number 7. This is equation number 7, and this is equation number 8. This is equation number 8, and this is equation number 9. Okay. Squaring and adding equation 7 and 8. Squaring and adding equations 7 and 8. Okay, we get u1 square plus b1 square cos square theta 1 minus 2u1 b1 cos theta 1 plus b1 square sin square theta 1 sin square theta 1 equal to b2 square cos square theta 2 plus b2 square sin square theta 2. Okay, or u1 square plus b1 square minus 2u1 b1 cos theta 1 equal to b2 square. But b2 square equal to u1 square minus b1 square. So u1 square plus b1 square minus 2u1 b1 cos theta 1, 2u1 b1 cos theta 1 equal to u1 square minus b1 square. u1 square minus b1 square. u1 square minus b1 square. Okay, r 2b1 square equal to 2u1 b1 cos theta 1. Okay, because b1 equal to u1 cos theta 1. This is the equation number 10. This is the equation number 10. Okay, this is the equation number 10. Okay, 2 is cancelled out by 2 and what b1 is cancelled out by b1, so b1 equal to e1 cos theta 1. This is the equation number 10. This is the equation number 10. 1 minute. The equation number 10 is b1 equal to e1 cos theta 1. This is the equation number 10a. This is the equation number 10a. Okay, this is the equation number 10a. 1 minute. 10a. Velocity of recoil particle. Velocity of recoil particle. Okay, recoil particle. Substituting b1 equal to e1 cos theta 1 in equation ix. Okay, in equation ix. Okay, b1 e1 cos theta 1. The velocity of recoil is b1 cos theta 1. Okay, e1 cos theta 1. Okay, and e1 square minus b1 square equal b1 square cos square theta 1 equal to v2 square, or v2 square equal to e1 square 1 minus cos square theta 1 equal to e1 square sin square theta 1, and v2 equal to e1 sin theta 1. Okay, it is called e1 sin theta 1, and this is e1 square. Okay, this is the equation number Hi11. This is the equation number 11. The relation gives the values of v2, the velocity of recoil particle, in terms of u1, the velocity of incident particle, and theta 1, angle of scattering, angle of recoil. Okay, angle of recoil. By the equation number 11, the relation gives the values of v2. The relation gives the values of v2, the velocity of recoil particles, in terms of u1, the velocity of the incident particle, and theta 1, the angle of scattering. Okay, angle of recoil, angle of recoil. Okay, dividing equation 8, dividing equation 8 by equation 7. By equation 7, we get tan theta 2 equal to b1 sin theta 1 upon u1 minus v1 cos theta 1. Okay, substituting v1 equal to u1 cos theta 1, we get tan theta 2 equal to u1 cos theta 1 sin theta 1 upon u1 minus u1 cos square theta 1 equal to u1 cos theta 1 sin theta 1 upon u1 1 minus cos square theta 1 equal to tan theta equal to cot theta 1 equal to tan pi by 2 minus theta 1. Tan pi by 2 minus theta 1. Okay, and tan theta 2 equal to okay, tan theta 2 equal to tan pi by 2 minus theta 1 and theta 2 equal to pi by 2 minus theta 1. Okay, this relation gives the value of theta 2. This relation gives the value of theta 2. Value of theta 2. This relation gives the value of theta 2. The angle of recoil in terms of the angle of recoil in terms of theta 1. In terms of theta 1, the angle of scattering relation 11 can be put in the form of theta 1 plus theta 2 equal to pi by 2. Theta 1 plus theta 2 equal to pi by 2. Okay, by the equation number 11. By the equation number 11. Okay, by the equation number 11. Okay, and by the relation, this relation shows that if the incident particle collides with a target particle, that means if the incident particle collides with a target particles collides with a target particles collides with a target particles of equal mass of rest at rest in the laboratory frame the both the particles moves in both the particles moves in direction perpendicular to each other. Both the particles move in direction perpendicular to each other. Perpendicular to each other after an elastic collision. After an elastic collision. Okay, center of mass frame. Next is center of mass frame.